Welcome to the fourth method of hydrologic routing. This is known as standard fourth order Runge method, or in short SRK. So as you know that pulse method and Goodrich method of level pool routing or hydrologic routing is basically a graphical method, and if you want to find the desired parameters, you have to depend on the manual interpretation of the graphs that depicts the discharge versus elevation or area and storage versus elevation graph, and if it is available you can find the important parameters of the hydrograph that will ultimately predict the outflow hydrograph from the inflow hydrograph. As you know that routing or flood routing is basically refers to the way we predict the outflow hydrograph with the help of the data of inflow hydrograph. That is basically known as routing. If it is reservoir, that means inflow to reservoir, you have that data, and you want to know the outflow hydrograph from the water coming out of the reservoir, that is reservoir routing. Channel routing, a flood has entered in the upstream. You have all those initial data when the flood has entered the channel, and you want to predict the hydrograph at the downstream when that flood reaches downstream. So that is channel routing. So there are various types of routing, and we are now discussing one of the method of hydrologic routing basically, and that is known as standard fourth order Runge method, or in short SRK. And this is the first computational method used for determination of the important parameters which are necessary for predicting the outflow hydrograph. So how to find the outflow hydrograph with the help of inflow hydrograph and with the help of SRK method. So you will be given the inflow data, inflow discharge at t is equal to 0, that means the initial time, then outflow at t is equal to 0, water level or elevation at t is equal to 0, storage at t is equal to 0, and of course time t is equal to 0. The initial time is represented by t0, t subscript 0. And of course, and also you will be provided the del t, the length of time step, the time increment. Basically what will happen is you will be provided the data of inflow hydrograph. By referring to inflow hydrograph, I want to say that the data is like this. The moment the flood enters into the reservoir, we start our time scale from 0, And after then 6 hour, 12 hour, 18 hour, 24 hour, 30 hour, 36 hour, then 42, 48 hour. So these are all in hour, and every time step you see or time increment is of 6 hours, right? And the corresponding discharge that is coming in, inflow discharge, will also be provided. The unit of the discharge will be meter cube per second. So as it is in meter cube per second, it is better to convert this 6 hour into the second. Convert the hour to second. So let us say at 0th second, 10 meter cube per second, 40 meter cube per second, 80, 120, 240, then it reduces 150, 100, then 50, then again 10. It may be other difference, but the flood generally, hydrograph generally follows the bell pattern, as we all know. So if I draw this hydrograph, and if this is the Q and this is the T, this will be your peak, and this is actually the time to peak, this from 0 to the peak time. This is T, time to peak. So we say that TP, and this is actually QP. Q subscript P, T subscript P. And this is your inflow hydrograph or inflow flood. So from this data, you have to find out what is at the outflow hydrograph, correct? So that outflow hydrograph will be somewhat like this. And you see, of course, the peak will diminish because of the channel resistance or reservoir resistance. And this is known as attenuation. That means reduction of peak. The amount of discharge reduced is referred as attenuation. And this time to peak also will increase naturally, right? So this part is known as lag. These are all discussed in my previous video on flood routing. So here what will happen, you will be provided this data, flood hydrograph data, and you will be so what mode you will be provided? You will be provided a graph of Q versus elevation, and also the area. This area is your surface area of the reservoir, not the watershed area or anything like that. It is the area of the surface of the water stored in the reservoir. So area versus elevation will also be provided. These are two graphs. Okay. Both have the common base or common x-axis, that is elevation. Now, if you observe the inflow hydrograph or inflow discharge or outflow discharge or storage, you will find that each of them is basically a function of the water elevation. Okay, let us not consider inflow here, because inflow will depend upon something else outside our area of interest, because the inflow comes in to a reservoir and then the outflow goes out when reservoir opens its gates, correct? So inflow will mainly depend on the time. As the time goes, the inflow will change, certainly. Okay, like you see now, this is the 0th hour, 10 meter cube per second, but at the 6th hour it is 40, then 12, then so on. And these discharge are measured in the inflow point only, at the inlet point. So at 0th second we find that the discharge is of 10 meter cube per second. So after 6 hours we find that discharge at the same point is 40 meter cube per second. After 12 hours we find that the discharge at the same point is 80 meter cube per second. So there is a discharge gauge that is located at the inlet of the reservoir, and it is measuring the discharge. Okay, so that is your inflow discharge, and from that if I draw a Q versus T curve, that is your inflow hydrograph. Okay, but other than this inflow, you see, take the example of the outflow Q. So when the water level of a reservoir is in this place, you see, H, so this is 1. So the potential energy stored in this H1 will be converted to kinetic energy when this gate is opened. So a certain amount of discharge will take place. But if this water level is increased due to the incoming water from that inflow flood, let us say H2. So for H1 we have a discharge of Q1, and for H2 we have a discharge of Q2. So you will find that if H2 is greater than H1, then Q2 will also be greater than Q1. Because the potential energy stored in H2 is greater than the potential energy stored in H1. And when it is converted to kinetic energy, H1 produce Q1, H2 produce Q2. So as H2 has greater amount of potential energy, then Q2 will be higher compared to Q1. Right? Okay. So this proves that Q is a function of elevation or water level or whatever you say. Again, this surface area, you see, the surface area of the stored water in the reservoir. Just see it. If the reservoir is like this, suppose this is a reservoir. So when the height is H1, you see the radius of the surface is R1. But when the water elevation increases, the radius also increases certainly. When the water level decreases, the area or the surface area, the radius of the surface will also decrease. So area or surface area of the reservoir also depends upon height or height of the water level, and also the storage. Of course, storage is basically elevation represents storage. If you multiply the surface area with the elevation, you have the volume of water stored in that reservoir. So if H changes, it increases, storage will increase. If H decreases, storage will decrease. So it is very clear. You can say that this outflow discharge, surface area and storage all are a function of water elevation or H. Okay, so if you have to find, the question will be find Q T at each T plus del T. That means, T plus del T means this is your input and you have to find the QT also. So if you want to find the outflow hydrograph, you must know what is the outflow discharge at 0th second and what is the outflow discharge at 6th hour, at 12th hour, 120th, 240th, 6th hour, 12th hour, 18th hour, 24th hour, 30th hour, 36th hour, and all this. At each time point, what will be the outflow discharge? You have to determine that. Then only you constitute the outflow hydrograph. So how to do that? So here I have already discussed that this S, Q both are a function of H. Surface area of the reserve is also a function of H. Outflow is also a function of H. And from the continuity equation we can deduce that if equation 1 is your continuity equation, I minus Q equals to ds dt. Right? The inflow of water, outflow water, what remains is the storage. Both I, Q changes with time, certainly. So storage also changes with time. This is actually the from continuity equation. Now again, I have just now discussed that if you multiply surface area with the water level, you will have the storage. So this is what they are saying. ds means incremental change in storage. So dsc will be equals to A multiplied by H, and area, surface area of the reservoir is a function of H. That is why A is a function of H. And dH you multiply the change in height. You multiply surface area with change in height, you get change in storage suddenly. So here you see Q is a function of H and I is a function of time. I have just now explained that. And so if you minus the change in or the storage from this inflow, you will find the outflow. So how it is coming, let me first, I'm not going too deep, but let me just give you an idea. So what will happen is, this I minus Q is equals to ds dt, that we all know. So here what will happen, we can change this equation 1 to I function of time minus Q function of H. Okay, and this, instead of ds dt, we can write A function of H multiplied by change in height dH divided by dt. Instead of this numerator ds, as ds is equals to H, A function of H multiplied by dH, we can write that here. Okay, so that will give you the equation 3. Not exactly the equation 3. For equation 3, what you have to do is you take this, you have to rearrange this equation, and you can find this one. Just take this IT to RHS, right hand side, and this QH will remain there, and you have to take the minus as common, so it will give you this equation. QH equals to IT minus H dH dt. Matlab, or you take this LHS, this one, this part, to this RHS to LHS, so it will become IT minus this one, this part, let it be X. So Q IT minus X and you take this minus QH to the RHS. So IT minus X equals to QH, it will come. Now you rearrange. So if you rearrange, you will get this one, equation 3. Again, if you rearrange, you see, if you again rearrange, you will find that if you take this part only, this earlier version of the equation, IT minus QH is equal to AH dHdt. If you just take this equation also, and if you place this AH into the denominator of the LHS, IT minus QH, just place this H, this area, to the denominator of the LHS, this inflow minus outflow, then you will get this one. This is known as equation 4. So basically what will happen is that this will give you a function of function which depends upon the time and elevation of the water in the reservoir. Is it so? This is inflow is a function of time, discharge, outflow discharge is a function of elevation, and so is your area, that is also a function of elevation. This will be equal to the change in the elevation with respect to time. So if from the very continuity equation and from this relation, equation 2, ds equals to a into dh, where a is also a function of h, and certainly if change in dh, if you multiply that change in dh with the surface area, then it will give you the change in storage. So from this equation 1 and equation 2, if you rearrange, that means if you place this QH into right hand side and this ADH dt into the left hand side, then you will get the equation 3. And if you from equation 1 and 2 and this equation, if you just place the area into the denominator of the left hand side, then you will get this one. And this is more important than equation 3. So what this equation states? It states that the change in water elevation with respect to time is equals to the inflow, which is a function of time, minus the outflow, which is a function of height or elevation, divided by the surface area of the reservoir, which is also a function of elevation. That means this entire expression, this RHS, is a function of T, time T, and water elevation, capital H. Now what this SRK method says, if that is the case, then the water elevation at the next time increment or next step, if this is your HI, the current step is HI, then HI plus will be the next step or next iteration. As I have said, SRK is an iterative method. So if we are I represent the current iteration, then I plus 1 represent the next iteration. So that elevation for the next iteration will be given by the elevation at the current iteration plus 1 by 6 multiplied by k subscript 1 plus 2k subscript 2 plus 3k subscript 3 plus k subscript 4 and multiplied by del t, the time increment. This constitutes the equation 5. Now you will say, what is k subscript 1, k subscript 2, k subscript 3, k subscript 4? What is that? So this k subscript 1 represent actually this one. Equation 4 is your K subscript 1, nothing else. T at current iteration, elevation at current iteration, that is your K subscript 1. So K subscript 1 is the equation 1 here, sorry, equation 4 here. What is K2? K2 is also equation 4, but this dependent function I, which is a function of time t, will now be a function of time t equals to t plus del t by 2. T means the t at current iteration plus del t by 2. And this dependent function q and area, surface area, A, will be a function of water elevation, hi, but now hi has been changed to hi plus half K subscript 1 multiplied by del T. And what is this K subscript 1? It is the equation 5.1 or this one. Similarly, K subscript 3 is nothing but that same function, but the time t is now ti plus del t by 2, and water elevation h is now hi plus half k2, k subscript 2 multiplied by del t. What is K subscript 2? It is nothing but this one, equation 5.2. And similarly, K4 will be the same equation 4, but instead of it depending upon T and H, it will depend the dependent function I, Q and A, or inflow, outflow and surface area, is now a function of Ti plus del T. Ti means the T at current iteration, and Hi plus K3 multiplied by del T. K3 means this one. Here also K2 means this one. And K this one. But the equation or this function TH is basically nothing but, or K1 is nothing but this equation. Matlab equation 4. Equation 4 is the K1. Then equation 4, which is a function of T and H, will this function of, instead of T, it will be Ti plus del T by 2. And instead of H, it will be Hi plus half K1 del T. So this change will just happen. T and H will just change. And then K3 also is the same thing. T and H will change. Along with H will become Hi plus half K, this 2 multiplied by del T. And in case of K4 also, the T will change. T will become T plus del T. And this H will become your H plus K3 multiplied by del T. So basically K is equation 4. That means equation 5.1 and equation 4 is same. Then 5.2 will come from 5.1 and equation 4, just change the T and H. And similarly 5.3 and 5.4 will come. Just change the T and H according to this relation. So you will get a new H. Hi plus 1 means a new H you will get nothing else. New H, that means the new elevation, water elevation. Now as you have the graph in between, or the relationship curve between Q versus H and A versus H, and now you have got a new H. You can use the train function of the Excel or just the graphical, draw a perpendicular from this new age to the y-axis or to the curve, onto the curve, and then from that point to the y-axis. In both y-axis, the y-axis representing Q and the y-axis representing the area. So that point will give you the Q or the new Q at the new age. And similarly, once you get a new Q, once you get a new A, you know this is an iterative process. So we'll again go to equation 5 to find another new age. Only thing is that this I and this Q will now carry the that current HI is changed, because this new HI will become the current HI in the next iteration, and so you have to find another HI from this relationship. So basically what happens from HI and your this equation 5, you will get a HI plus 1, and from this HI plus 1 you will get a new Q I plus 1 and new A I plus 1. And using this Q and this new Q and new A in equation 4, and using this equation, what is this equation? This is the equation 5. You will find the equation I plus 2. And again from HI plus I plus 2 you will get a new QI plus 2 and a new AI plus 2. You put it in the equation 4 and you get this equation 4, and then you get equation 5 and its corresponding equations 5.1, 5.2, 5.3, 5.4. Then you get HI plus 3. So constantly what will happen is you will get the Q. The Q that you get will help you to draw the outflow hydrograph. And once you find the outflow hydrograph, you can find what is the attenuation and what is the lag. So that is all you have to do. But the thing is that you can easily note that this is basically a complete iterative process. Okay, so from equation 4 and equation 5, you get new H's. You just from new H you get new Q, new A, put it into equation 4, again a new H, and so on. So this is basically what is known as SRK method or standard fourth order Runge Kutte method. Okay, so with this I'll finish this video. If you like it, you subscribe and click on the bell icon so that whenever I post a video you get an alert. And for any confusion you can comment to this video. I will try my level best to solve your problems. So you may also like this newsletter Hydrograph, where I post latest news, startup ideas, new journals, new conferences, and various other interesting topics, case studies based on the hydroinformatics engineering. So hydroinformatics engineering is nothing but the application of AI and data science in water resource development. And if you want to enroll to some smart courses, you can go for vaipatra.ws and enroll for the very short-term courses there. Energy in Style will help you in participating in internship. And now online and offline both type of internship is available. But offline is not free, sir, because you have to go there and stay and do the work. And there are various books and items related to subcomputing and engineering in my Gumroad shop, Innovates. You can go there also and subscribe it, such that you can receive a regular updates. And you can also earn money from selling these subcomputing books and items if you enroll as an affiliate of my shop. And this is my latest book, 2 books, 7 meta heuristics to learn for your next data science project, and Introduction to Model Development for Prediction, Simulation and Optimization. These are the 2 books that I have just published, and they all are related to the application of data science, meta heuristics, AI into different problems of water resource development. And ultimately, just 1 or 2 weeks ago, I published this book, 10 case studies on vulnerability assessment in water resource development. It is all about vulnerability assessment with the help of different MCDMs, nature-based algorithms, bio-inspired optimization techniques, and mainly here I have dealt with the climate change and urbanization vulnerabilities, not other vulnerabilities. So you can have a look into this book also. It is available in Amazon and also in Notion Press. All these 3 books are actually available in Amazon, Notion Press, Gumroad, this thing. So if you want, you can procure them and read it. So thank you for now, bye for now, and I will come back with a new video on the next flood routing method, which will be under hydraulic routing. Until now, I was discussing about hydrologic routing. Now I will discuss about hydraulic routing. So goodbye for now. See you at that time.